I guess it is my pleasure to invite our next speaker to start sharing his slides. We have Matthias Volk here, going to tell us about the geometry of Feynman integrals in Twistor space.
Yeah, okay. Thanks a lot for the invitation to present at this very nice conference. So I'm going to present this paper here from May that was written together with Christian Vergu from Copenhagen, and that's also building on top of previous work and still ongoing work with Jake Berjali, Andrew McLeod, Matt van Hippel, and Matthias Wilhelm. So the title is Geometry of Feynman integrals in Twistor space. And so basically what we're going to do is we're going to analyze the geometry that we can associate to a certain class of Feynman integrals. And yeah, contrary to what we see now, we're going to do this in momentum twistor space. Okay, so for the context here, of course, we're interested in Feynman integrals for scattering amplitudes. For example, we can imagine a really nice theory like n=4 super Young mills. And as it's well known, if we look at simple amplitudes, then many times they can be expressed in terms of relatively simple functions. So in particular, these multiple polylogarithms that we've also seen a lot now over the week. So these functions, they're of course relatively well understood, although maybe it doesn't necessarily mean it's very easy to work with them, but at least the definitions are kind of clear and so on. But it's also, okay, the whole point of the week is to discuss about the fact that we need more complicated functions, and that when we make more complicated scattering amplitudes, that we are going to expect more complicated integrals. And many of these more complicated integrals, then they often have some interesting geometry, as we've seen now so many times, in particular some elliptic curves, or free surfaces, or some Calabi-Yau manifolds. Okay, so basically some questions that we have to address is, first of all, if we have some Feynman integral, how do we associate the geometry to this? And also here we've seen already some ways to do this now. We've seen many of these parametric representations. And so now what's going to be the focus of this talk is to not do this parametric representation, but to construct some geometry directly in a space that's more physically motivated, which is this momentum twistor space. And then also, okay, when we have some geometry, of course, we would like to analyze it a little bit. So that's also what we're going to do. Okay, so basically the plan is there will be a brief introduction, and then I will focus on this particular class of integrals, these train track integrals. So these are basically generalized box integrals. And the main results are going to be that for the two-loop integral, we're going to construct an elliptic curve. And this curve will arise at the intersection of two quadrics in a three-dimensional projective space. And for three loops, we're going to construct some surface, and this surface will be some fourfold cover of product of projective lines. And then I will say a bit more about higher loops, how we can always get some Calabi-Yau as a complete intersection there. Okay, and then I will conclude and give some further directions. Okay, so let's begin. So first, I'm going to review briefly how we can find a geometry for a Feynman integral. So again, what we imagine is we have some Feynman diagram, and we just apply the Feynman rules that we know for theory, and we get some nice integrand. So we can also get this integrand maybe in some other way, but we imagine we have some nice integrand, and then we have a bunch of loop integrations that we have to do. So what we can now do is we can just apply the textbook procedure. So we can introduce some Feynman parameters, and we can start to integrate. So integrate, it means, okay, we're going to try to express this in terms of functions that we know, which would be these polylogs. And this can go well for a number of times, and then at some point, maybe the process is going to stop. And we're going to end up with something where we have a bunch of polylogs, and then it's going to be multiplied by some nice form that will live on some geometric object. So it will live on some variety. So the easiest example is, okay, I introduce Feynman parameters, I do a number of integrations, and then what I'm left with is still some integration to do, but in my denominator, there's going to be the square root of some cubic polynomial. So now clearly it doesn't fall into this class of polylogarithms anymore. So what I would conclude is that there's an elliptic curve that will be defined by this equation here. Okay, so that's how we can do this direct integration method. That's the one way to do this. And then we can also kind of take a shortcut here, because we can say maybe we don't really care about all these polylogs, but if we just want the geometry, we can also get this form by taking residues. So that's the second approach here. So basically, we can again start with this integrand that we have, and we imagine it's a product of some propagators. So there are some poles. So we can start to take residues around the poles. And again, this works a number of times, but then at some point the process will stop because we cannot take any further residues. And then we land on this residue of the highest codimension, and which is going to be this leading singularity. And typically, if this leading singularity just consists of some constant, well, like in a sense, yeah, of some constant, then I would conclude that the integral is probably going to be polylogarithmic. So in the following now, we're always going to look at this leading singularity, and we're going to analyze it. So we will always be interested in taking residues, essentially. But okay, so we don't want to do this by introducing some parameters, but we want to do this in terms of momentum twistors, as I said already earlier. So I will just briefly remind of this, how this works with momentum twistors. So again, we imagine we have some Feynman diagram, and of course there are some momenta, some external momenta sticking out. So now we can repackage basically all this information in some nicer variables. So we can first of all switch to the dual coordinates. So they're just written here. And then we can also go further and we can introduce these momentum twistors. So they were then introduced by Andrew Hodges. So so the momentum twistors, they're just some points in a three-dimensional projective space. And then what one can work out is how all the objects that we talk about in momentum space are mapped to momentum twistor space. So in particular, if we have some point, so it could be one of those external points or one of these internal points, it's going to correspond to a line in the three-dimensional projective space. So yeah, so there's going to be a line that corresponds to a point. And then also this distance of 2 points, so x minus y squared, it just becomes the 4 bracket in P3. So we just take the 4 by 4 determinant of those 4 points. So now what I said is, okay, we want to take residues. So in particular, since in this dual space, the propagators, they are essentially just the distance between these 2 points. We will always be interested in this case when the separation between these 2 points is 0, so when they are lightly separated. And then geometrically, what happens there is that these 2 lines, they meet in a point. So that's what we're going to need now all the time. And yeah, okay. Also, I forgot to say something. Of course, these dual coordinates, they're nice for various other reasons also, because if we imagine that we do this analysis for some amplitude and n equals 4, then they expose also this dual conformal symmetry. So we can also imagine that on this axis, we actually have some conformal group acting maybe. And yeah, then these conformal transformations, they just become the coordinate transformations in this P3. Okay, so now, as I said, we want to apply this dictionary here over and over again to analyze this leading singularity. So the easiest example will actually be this box integral. So this was already done by Andrew Hodges. So here this is the box integral. So so for now and also in the following, the graphs in black, they're going to be some graph, some Feynman diagram in momentum space, and then behind it is the dual graph. So and also the integral is written up here. So massive, I mean that the corners here are going to be massive. And now I want to apply this dictionary. So I have 4 external points, 1, 2, 3, 4. So if I want to draw the picture, what this corresponds to in this P3, then I should draw 4 lines. So I should have 4 lines, and they are supposed to be skew because these corners are massive. So for example, we have x1 minus x2 squared is not equal to 0. So they're going to be skew. So this all just also follows from this dictionary. Okay, now I should find also a line that corresponds to this point in the middle here. But since I'm interested in this leading singularity, I should demand that this point is slightly separated from all the other points. So geometrically, I should find a line that intersects all these other lines, right? Okay. Okay, so now, as I said, this analysis, it was done by Andrew Hodges, and you can find that to this problem of putting the lines in this way, there are basically, there are two solutions that are characterized by some cross ratios. And the point here is, okay, so we get these two solutions for this problem. So in the end, what we conclude here is that there are exactly two configurations where all these dual points are going to be lightly separated. So what we conclude here in the end is that this leading singularity space that we're interested in, so in this case, it would just be 2 points, right? So here it's not so interesting really, but of course, now then when we go to now the more complicated examples, it's useful to remember that that's kind of what we're after. Okay, so now we can look at these more complicated integrals, these train track integrals. So as I already mentioned, these are basically a bunch of box integrals that are next to each other. So again, that's drawn here now. And in particular, they were studied by these people in 2018 a lot. What they did was they used this method that I said earlier. They used this direct integration approach. So they introduced some Feynman parameters for some nice conformal integrand, and they started to integrate in terms of polylogarithms. And then they found, in the end, they couldn't continue doing more integrations, and they concluded that the geometry that's associated here to this integral would be given by some hypersurface in a weighted projective space. And to be more concrete, in the case of 2 loops, they found an elliptic curve. For 3 loops, they found a K-free surface, and for 4 loops, they had some Calabi-Yau threefold. Okay, so now the first thing that we have to do is we want to look at this 2-loop case here and also find the elliptic curve. But again, we don't want to do any integrations, and we also don't want to do this these Feynman parameters, but instead we just want to apply the dictionary and kind of do the analogy similarly to how this works for the massive box. Okay, so that's what we're going to do now. And so here I'm just drawing 1/2 of the integral for now. Well, 1/2 of the diagram really. So you should imagine there's going to be another box here to the right of it. And now we're going to just start putting the data in P3. So we have these 3 points, x1, 2, 3. So we should have 3 lines, 1, 2, 3. These are the red lines over here. Oh, P3. These are the red lines over here. So, and they're skew. They're going to be skew because again, these corners are supposed to be massive. And so now the first result that we can use is that when we have three skew lines, then they determine a quadric in P3. So that's this blue space here, and you can also give the equation. So the equation is written here. And now we can invoke also some fact about quadrics. So a quadric, it's a ruled surface, so we can find different families of lines on this quadric. And if we take some lines that come from the same ruling, then they're going to be skew. So these would be these red lines, for instance. And if I take 2 lines from different rulings, then they're going to intersect. So that's convenient because, again, we still have to find a line that corresponds to this loop point here. But since we're interested in the leading singularity, this point should be lightly separated. So the corresponding line should intersect all the other lines. But so it means we can just take it to be from the other ruling. So this gives us a way to say where this green line should come from. Okay, so that's how we first for 1/2 of this integral or 1/2 of this diagram really we construct a quadric. Okay, so now we want this 2-loop diagram, and so now we have to do this twice. So we get 2 quadrics. So again, for this half of the diagram, that's going to be quadric, and there's going to be another quadric for this half over here. So we get 2 quadrics, this QL and QR. And now we just have to take care of one final constraint, because we should also, for the leading singularity, ensure that these 2 points here the two loop points are light separated. And so this can be done by demanding that these quadrants intersect. So that's shown here in this picture. And again, so now we have already constructed the elliptic curve, because it turns out that if we have two quadrics in P3, then the intersection is an elliptic curve. So that's how this elliptic curve can arise here. So we just built two quadrics, they have to intersect, and the elliptic curve is there. And we didn't have to introduce any parameters or Feynman parameters. Okay. So now we should also analyze a bit this curve. So maybe we want to have some form on this curve to be able to integrate. So the way this can be done is we can start with the form that we know in P3, the normal form in P3, and then we can take residues with respect to this quadric. And one can easily check that has the right rescaling weight and all that. Okay, so another thing that we are interested in is we want to characterize this elliptic curve, and we know for when we have an elliptic curve, there's only going to be one modulus. So this is this famous J invariant. And so what we can do here is we can compute the J invariant. So here I'm just giving the formula for the J invariant that we have. So this is the formula, and this Z here is some cross ratio. And I'm not writing how it explicitly depends on these quadrics, QL and QR, because yeah, it would take too much time to write it now. But the point is that, okay, we can basically fix some external data. So we can fix some momentum twistors, and we can compute these quadrics, and then we can compute this Z, and we can compute the J invariant. So it can all be made very explicit. So yeah, we can compute it basically. And okay, so why is it useful to compute this? Because also it allows us now to compare. So this integral that I said, this double box integral, it was analyzed many times before, and in particular also it was particularly also analyzed in this paper, where again people did this direct integration approach using Feynman parameters. So they had some nice rational integrand and did a bunch of integrations, and in the end they had something that was dx over square root of a degree 4 polynomial times some polylogs. And they defined some elliptic curve in this way by this equation here. And for this, you could also compute some J invariant. And so now here we did something quite different in the sense that, okay, we didn't introduce any Feynman parameters, and we didn't do any integrations, but we just, okay, did this elliptic curve, it just arose as the intersection of these two quadrics. And we also have a formula for the J invariant, and we can compare the two, and they are the same. So that's the first result, basically, that we find that these two descriptions, they match here. Okay, and that's of course very nice, because I guess if we want to talk about the geometry of some Feynman integral, the best thing would be if it doesn't really depend on how we parameterize the integral. Okay, so that's the elliptic curve, or this double box integral. So now we can start to add more loops to the picture here. So okay, so first now we again want to look at the leading singularity of this 3-loop integral, and we want to construct this in momentum twistor space. So first we can of course recycle what we already know, because we know that if we have one of those boxes here at the end, we're going to get a quadric. So there's going to be these two quadrics. So there's one quadric here for this piece on the left, and there's going to be a quadric here on the right. And now we just have to take care of all this data here in the middle. So the way this can be done is, again, to this x1 and this x2, we should put a line each. So we're going to have a line here and another line here. And now we have to also find a line that corresponds to this loop point here, this point in the middle. But again, since we're looking at the leading singularity, the point should also be light separated from the red point. So the line should intersect. So it should cut through these red lines. So we can take actually a point here on each of these lines and say that we just parameterize the line in the middle in this way. So, okay, now I've drawn it a bit badly, but it should go through these points, of course. Okay, yeah, so here's the picture. It's drawn much more nicely. So again, we have a quadric coming from the end. We have these lines L1 and L2 that corresponds to the external points. And we have this green line that corresponds to the middle loop point. Okay, and now we can, at this point, we can actually invoke Bézout's theorem. So now we can say, okay, this line, this green line, since we're assuming that everything is in completely general position, maybe something I should have mentioned also, we're assuming that everything is in completely general position. We can assume that this line, this green line, is going to intersect each of the quadrics in 2 points. So that's very nice, because then it means that also this last constraint that for instance, this point and this point are going to be lightly separated, it can also be fulfilled. And in particular, it can be fulfilled for any choice of these points P1 and P2. So that's actually the next point. So now at this point, we just basically put all the data in P3, and now we have to see that what I'm saying is that this leading singularity locus, it's a 2-dimensional space. So that's the first thing we have to see, because I'm claiming there's some surface. Okay, so the way this can be seen is again that we can actually choose freely these points that we use to parameterize the middle line, and we can still satisfy all the constraints that all the points are lightly separated. And this is just because, as I said, by Bézout's theorem, the middle line will always intersect the quadric in 2 points. So it's definitely going to be a 2-dimensional space. And then we can say a bit more, because, okay, so let's say we have fixed these points, P1 and P2. So we fixed this point and this point on these lines. Then we still have different choices for the intersection points of the quadrics. So, oh, sorry, I went in the wrong direction. Sorry, yeah. So I don't know, I can, for example, choose this one and this one, or I can choose again this one and here the other one. So in total, there are 4 choices for these intersection points. So in total, we can say actually we have a 4-fold cover of P1 times P1. And yeah, these P1s, they correspond exactly to these lines here. Okay, so in total, we have this 4-fold cover of P1 times P1. And it's also, okay, so the situation is kind of similar for how you can also have an elliptic curve in the plane. So the way we can have an elliptic curve in the plane is, okay, we take some P1 and we take 4 points and we fix them to 0, 1, infinity, 3 of them. And then we just have this last one left, this lambda. And then we can write an elliptic curve in this way. And this curve is a double cover of P1 branched over 4 points. So here again, the situation is kind of similar, except that we don't have a curve branched over some points, but we have a surface branched over some curves. So what we should do now is we should look at what are these branch curves. We should look at basically the analog of these points in the case of the elliptic curve. Okay, so the way this is done is we have to remember what was the reason for why we had different branches in the first place. And that was, of course, because we had different choices for the intersection points. So again, we had these quadrics, and the green line was going somewhere here, and there were different choices for the intersection points here. But now, of course, if the line maybe becomes tangent to the quadric, then there's going to be less branches. So in particular, let's say it's tangent towards this, towards on the left quadric, then there are only going to be two choices left here. And so we can compute when does this happen. So and we get these 2 equations. So for example, if the first equation is fulfilled, then this green line is going to be tangent on this QL. And if the second one is fulfilled, it's going to be tangent on this QR. Okay, so in total, we get these 2 curves, this delta L and delta R. And we can also see, since these are quadrics, they are by degree 2, 2, and they live in P1 times P1. So from this, we can conclude that they're actually themselves elliptic curves. And yeah, also, okay, the second point I already said here, because as I said, if we are on one curve but not on the other, then there's still 2 branches left. But then there's also the situation where they intersect, and it turns out they intersect in 8 points, and there we only have 1 branch of the surface. Okay, so this is also summarized here in this table. So again, if we're on the intersection of these two curves, then there's going to be 1 branch. If we are just on 1 curve, then there are 2 branches, and yeah, in the rest of the space we have 4 branches. Okay, and so we can use this information to compute also the Euler characteristic of this surface. So it can be done using the surgery property of the Euler characteristic. So one has to use, for example, also here it also enters that these curves, they are themselves elliptic curves, so the Euler characteristic is 0. And indeed, for this K-free surface, we get that the Euler characteristic is 24. So so this is also expected, of course, because yeah, so we know that the Hodge numbers for the K-free, they look like this. So this Hodge diamond looks like this, and this Euler characteristic is just the alternating sum of this Betti number. So it should be 24. Okay, so that's correct. And yeah, so here we just computed it directly. Okay, so a few more things we could do is we can look at the dimension of the modular space here. So this can be done by basically counting parameters. So essentially, in this case, you kind of have to take these 2 curves, delta L, delta R, and you have to count, okay, how many curves are there basically that intersect in 8 points. And we find that the dimension of the modular space here is 11. And now for K-free, this is nice because we know that this is also related to the pK number of this K-free surface, because they should add up, well, sorry, so the pK number and the dimension of the modular space, they should add up to 20. So in this case, we should get that the pK number is 9. We can also write a holomorphic form like one does for the elliptic curve, basically. It's just written here. And one more thing we could look at is some kind of symmetries of this construction. So we can look at some involutions of this K-free surface. So in particular, we look at these Niculian involutions. So these are some involutions that basically don't change the holomorphic form. And then there are some nice theorems by Niculian that tell you that if you know something about the number of fixed points of this involution, then it gives you bound on the pK number. So in our case, we found such an involution. So yeah, we found such an involution, and it turned out to have 8 fixed points. And then we could look up in these old papers that the pK number has to be greater or equal to 9. So it's actually perfectly consistent with the analysis also that we did here, and it seems like this bound is satisfied. Okay, so that's for the K-free, and so now there's an important open question. So right, so for the elliptic case, we could just easily compute the J invariant, and then we could compare it to this construction that people did in the to this hypersurface in weighted projective space. So now we would like to do this here, but we don't really know how to do this at the moment. At least I don't know how to compare if this is now the same K-free surface or not. That's something that would be interesting. Okay, so now we can again add more loops to the pictures, and now I'll be a bit brief. So again, we have 2 quadrics, obviously, that we already know. We get this from the boxes here at the end. And now we take care of all the data in the middle. So we have to these dual points, we put these lines, L1, L2, and L3 and 4, and so on. And again, we put the green lines corresponding to these points here in the loop. And then, okay, at this point, we just have to also impose one more constraint, namely that these 2 points are lightly separated. So there's a constraint here, and that amounts to imposing another constraint in P3, namely that these green lines, they intersect here in a point. And again, you can see that this is going to be 3-dimensional space, because there are these 4 lines, and basically impose one more extra constraint. And yeah, it's also okay. At this point, you can also see that this is going to generalize. So you can iterate this procedure now. You can keep adding these lines and demand some intersection. And so in total, we can actually always build for these train track integrals here. We can always build this Calabi-Yau manifold as a complete intersection that could be embedded in some toric variety. So the usefulness of this is maybe that you can use some combinatorial description. That's in particular this Baturas-Borisov construction of Calabi-Yaus to compute some data about them. So you can compute some Hodge numbers, for instance. And for this picture that I showed now, so for the for loop diagram that's supposed to be Calabi-Yau threefold, we did it. So we computed some numbers and the Euler characteristic with this computer program pipe. The problem is that to actually compute something here, it also actually quickly becomes kind of impossible because the combinatorics they also grow quite badly. So in particular, this is because the codimension in this embedding space here. So in this embedding space, it grows also with the number of loops. So in other words, we have many constraints that we impose. But the message is that for this general train track integral with L loops, we can always build Calabi-Yau L-1 fold. And the embedding space would have a dimension of 2L-1. So you can actually see that the codimension also is L-1. Okay, so yes. Okay, so that's okay, I'm doing fine with time. Okay, so then I'm already going to conclude here. So so what did we do here now? So we looked at this leading singularity of the train track integrals, but we did this in momentum twistor space. So not by looking at Feynman parameters. So so what we saw is that for the two loop, for this double box integral, we could get the elliptic curve as an intersection of two quadrics in P3. For three loops, we had this fourfold cover of this P1 times P1, and when we go to higher loops, we could see that we can add. We always have to add more equations, so we add more space and we add more equations in some sense. So, but just from how the equations scale, we can see that there's always going to be a Calabi-Yau in there. Okay, so why was it nice to do this in momentum twistor space? Or what was the usefulness of not introducing these Feynman parameters? So one point is that really all we ever have to deal with is kind of intersection of lines. So that's nice maybe then because I guess linear equations are a bit easier than quadratic equations, but of course it comes at the cost of having to impose many of them. Another nice feature is that we don't introduce any unphysical parameters. So we construct this geometry directly in a space that has, of course, also relevance in scattering amplitudes in general. So that's another nice feature of this. And finally, as I said, this in particular also in relation to amplitudes in n equals 4, that this conformal symmetry becomes manifest. Okay, so now first thing, so now some further things that can be done here. So first of all, one can supersymmetrize this construction. So Christian here suggested this, that one can supersymmetrize this whole construction. So basically the idea is that when you look at the amplitudes in n equals 4 superangles, then they're not only conformal, but they're actually going to be superconformal. And so if we analyze this leading singularity, maybe it's something that can even be respected there. And the way this can be done is you can basically do the whole analysis that we did again, but you formulate all these intersections that we have, all these intersections of the lines, you would formulate them in terms of some delta functions and that are going to be nicely invariant. And then at the end, it's very easy to supersymmetrize because you would just replace P3 by P3/4 and the delta functions by some supersymmetric version. that's one thing that can be done here and can also be, I guess, explored a bit further. So another thing is that we can also build more complicated diagrams. So for instance, we can build kind of like a fishnet type thing. So we can build like a grid of boxes. I'm saying fishnet type because of course there are more external points here. It's not just a 4-point, but there are many external points here. But then just from how this scales with the equations, we can also see that there's going to be some Calabi-Yau involved in there. And maybe another thing that can be done is to look at also massive internal propagators. Okay, so there's still a bunch of open questions. So one thing is definitely the generations of this. So because again, so if we have this such a train track integral, and we start to remove some of these legs, some of these external legs. So in other words, we're kind of collapsing we're making some of these dual points collide. Then at some point we're gonna see some ladder diagrams, and they have been computed a long time ago, and in particular in terms of polylogarithms. So at some point, what we should see is how this geometry degenerates to something much simpler. So and that should also work for these fishnet type diagrams, because they are eventually, if we start to remove external legs or dual points, we should find these Buster-Dixon integrals. Yeah, these fishnet integrals. Okay, so another open point is, okay, how are we going to deal with non-planar integrals? Because yeah, so now this was all done use this Twistor approach, so tied to planarity, but I guess it would be nice to also have a description for non-planar integrals, because we also know that there's going to be some Calabi-Yau for non-planar integrals. And then, okay, another point is the role of different parameterization. So now for this, okay, so we had this one example now for this double box integral, where we did this construction in Twistor space, and we could actually compare it to Feynman parameter way to get a geometry to this direct integration method, and it turned out to be the exact same elliptic curve. But okay, we also know that there are other representations of the integrals. So in particular, something that has come up a lot now in this week has been the Bykov representation. So and in general, we have to make sure that we get the same geometry there. And there are, of course, also examples where, in particular, this paper from last year, where people use different representations and they actually find different elliptic curves. So in this case, in this paper that I'm mentioning here, it's for the sunrise intervals, but of course, it would also be good maybe to see what happens in this for this double box integral. Yeah. Okay, and then another point is, one thing we haven't really used here is this Calabi-Yau mirror symmetry. So this has also appeared in the analysis that people do to describe some Calabi-Yau geometry that's associated to Feynman integrals. There have been various papers also here, and yeah, I guess maybe, I don't know, maybe even the next talk, I don't know, might also involve that, I don't know. Okay, yeah, so that's actually the end, and thank you. Yep.
All right, let's all take a moment to unmute ourselves to thank Matthias with a round of applause. And it looks like David has the first question.
Thank you, Matthias, for this wonderful talk. At every stage along your interesting journey, I saw the precise parallels with the multi-loop sunrise diagrams that I've been talking about. I mean, I saw elliptic curves, I saw the K3 surface, which I didn't talk about in my talk because it's already 15 years old, that comes from the 3-loop sunrise diagram, and I saw Calabi-Yau threefolds. You gave wonderfully explicit formula for your J invariant, just as I did, which is dependent upon Z, which is determined by some external kinematics. So the thing to look at is exceptional values, not singular values. not of the differential equation, but the exceptional values that I was talking about, where the problem becomes modular. And you can do that. You can look at your J invariant of Z and ask yourself, is there some particular kinematics in which your Picard-Fuchs operator, gives you smaller characteristic numbers? Not just look at the singular places, but regular places. So go to your J invariant, find some elliptic curve which is an elliptic curve over some Q, over Q, or as I was doing with algebraic numbers, and then go back and look at your Hodge numbers, look at them, and you'll find that you're at what Duco von Straten, who taught me this in Mainz 10 years ago, he calls them singular values. He calls them singular because they're remarkable, they're special, So you have down there, you take every slide of your talk and go back for your train tracks and your ladders and go back and look at my little toy example of sunrise diagrams, and then ask yourself, what are the special points? What are the places at which all your blow-ups and all the algebraic geometry you're doing becomes very, very special, very different?
Okay, I will go back and take a look. That's a really nice suggestion. Thank you. Thanks.
We also have a question from Karen.
Hi, I just wanted to ask, let's see if this will work for me to annotate on your screen. You had your fishnets. What if you take your fishnets and join them up this way? What do you know about those guys?
Well, so then it's not a planar diagram, right? So
no, it's not, but it's still got a lot of the same properties, right? Because it's almost planar in the sense that if you ignore the external edges, it's planar. So in the pure graph theory sense, it's planar, but with the distinguished vertices on two different faces instead of on one.
Okay, I can't say immediately what happens, but so do you have a suspicion, or do you
I know a tiny bit about C2. That's all. So I'm not as far as having a suspicion for you.
So for C2, you mean they're the same, or?
The C2 at 2 is 0, but then the C2 at other values is probably not.
Okay. Okay, I can't say right now because it doesn't look planar, so I have to think a bit harder, I think. But it's okay. It's a good suggestion. I think I will look at it. Thank you.
We also have a question from Lance.
Hey, nice talk, Matthias. Just a quick comment on that last figure. That's reminiscent of some work that Benjamin Basso did with Deliang Li in trying to make the fishnet graphs that we looked at more periodic, but he probably didn't do it in a graph by graph. But they may have looked at it a little different way. But if you're interested in that case, you might look at Basso and Li.
So you're talking about the graph that Karen drew, or?
That's right. Yeah.
Okay. Okay.
And I also wanted to.
Thanks.
Yeah, I don't know if you'll find anything useful in there or not, but it's one place to start. Another comment is just that, yeah, I think it's very interesting to look at these degenerations to polylogarithmic, because when it comes time to actually get numbers out of these integrals, you're going to have some differential equations, and you're going to need to fix them with boundary conditions. And this seems like a nice surface. These surfaces where the things degenerate to polylogarithmic seem like good places to fix the boundary conditions.
Yeah, indeed.
Yeah. And then a question was, have you thought about Yangian symmetry at all? Because a lot of these integrals, people have been exploring Yangian symmetry and differential operators that come from that. And can you see any of that from your side?
Okay, so I haven't thought so much about it, but I know that I think some of the other people in Copenhagen were thinking a bit about this, and I know I'm afraid I can't be more specific because I haven't thought about it so carefully myself. But I don't know, maybe Christian knows more, or also Matthias. I'm not sure. I'm sure some people mentioned this before. but yeah, I guess we can also look at this.
Okay, thanks a lot.
We also have a question from Laura.
Hi, very nice
Hey.
talk. I have what's probably an ignorant question, but I was curious. You mentioned Calabi-Yau involutions, Nikulin involutions in the K3 case.
Mhm.
Is there any significance to discrete automorphisms of Calabi-Yaus for, say, Calabi-Yau threefolds or the higher dimensional ones?
Okay, so I'm sure there's something you can do because, okay, so this construction that we do, there are definitely some symmetries to it. So, but we haven't really worked this out. So, but okay, now that I think about it, I guess. So for the Nikulin involution, for instance, for the K3 case, it corresponded to switching these intersection points. So that's something I guess in principle you can also do for the higher dimensional cases.
Mm.
But yeah, I don't know. Maybe it could be interesting to work this out. I'm not quite sure at the moment.
The origin of my question is a lot of these symmetries have been classified for, say, Calabi-Yau threefolds. So I didn't know that.
Okay.
If they're actually available, then you could ask what their significance was.
Okay, that's a nice hint. I wasn't aware of this, but yeah, thank you. That's helpful actually. Yeah. Thanks.
And then we have one final question again from David, who is muted at the moment. David.
Yeah, there are so many sparks flying in my mind at present. You know, Lance has talked about fishnets, we talked about train tracks. Now, I'd forgotten that I'd done that work. You know, thank you very much for reminding me that in 1993, Andrei Davidichev and I did. But what Andrei and I did later, and it took us 10 years to do it, is we summed those massless off-shell ladder diagrams to all orders, and Andrew and Lance and the co-workers have done that for other diagrams. So we have a non-perturbative answer down there, and it's very, very simple, you know. I mean, so there's something here that you know you should be maybe. Hopefully, it won't take you the 10 years that it took Andrea and I to do it for all cross ratios, and because Andrew and Lance and co mopped up quite quickly. There's something down there. Okay, we're only looking at a tiny subset of Feynman diagrams down there, but we're making contact with the non-perturbative physics of people like Benjamin Basso. You know, deeply informed what Lance has been doing, and at the end of the day, the final results to all orders and the coupling constant, you know, when we have planar diagrams and the finite circle of convergence and all of the toy physics of n equals 4 super Yang-Mills. So, you know, look at these, look at this as a gem mine. Try and go to all orders. Might take you less than 10 years.
Okay, I guess thanks for the encouragement. Maybe, yeah, I mean, it would definitely be really cool to get some non-perturbative answers here. So, thanks, yeah.
All right, great. Well, those are some great questions. Now I guess we can thank Matthias again. And so next we have